We discussed question 6 of A-level mathematics paper 6, probability and statistics 2 in May or June of year 2020. T denotes the length of time that a passenger has to wait for a bus at a certain bus stop. We have the probability density function. Time is in between 0 and 20, and the density function gives us 0 for any other time. Part A, to sketch the graph of the density function. We consider the time in between 0 and 20 is 0 elsewhere, so it's irrelevant. F of t is 3 over 4,000. This is just a constant. Because you have a quadratic function, we can pull out a t, and then we have 20 minus t. We see that f of t is 0 when t is either 0 or 20. Set both of them to 0, and you get t equals to 0 or 20. Meaning that the vertex of the parabola is at 10. It must be the average of these two. So here 0 plus 20 divided by 2. The parabola has a vertex at p equals 10. This is also the axis of symmetry. And we need to find the y coordinates when t is 10. So we compute t of 10, here 3 over 4,000. We just use the factored form. That is a 10. 20 minus 10 is a 10. So we can cancel this, and we get 3 over 40. To sketch the graph, is 0 elsewhere. That is f of t, and this is t. And we have a quadratic graph that is perfectly symmetrical at t equals 10. So you have a parabola like that. Let's just assume that it is perfectly symmetrical. So from here, this is 20, that is 10, that is 0, and we have 3 out of 40 here. That gives you the graph of f of t. It is 0 elsewhere. Part B, hence explain without calculation why the expected value of t is 10. The mean is 10. The graph is perfectly symmetrical at t equals 10. Therefore, the expected value must be 10. Part C, to find the variance of t. The variance of any random variable is given by the expected value of t squared minus the square of the expected value of t. We know that the expected value of t is 10, so that would be the square of 10. And we still need to find the expected value of t squared. To find the expected value of t squared, the graph is non-zero from 0 to 20. Then we have t squared f of t dt. We just integrate with respect to t to find the expected value of t squared for a continuous random variable. T squared f of t. So you have 0 out of 20, and then we have 3 over 4,000. That will give us 20t minus t squared. You still need to multiply by t squared. We can pull out the constant 3 over 4,000. And then we just integrate 20t cubed minus t to the 4 with respect to t. That t squared we have to distribute. 3 over 4,000 remains. So upon integration, 20 divided by 4 is 5, t to the 4 minus 1 over 5 t to the 5, and we need to evaluate from 0 to 20. We have 3 over 4,000. Replace t with 20, you have 5, 20 to the 4, minus 1 over 5, 20 to the 5. When t is replaced with 0, we just have 0 throughout. So we don't bother with that. That gives us a value of 120. Therefore, the variance of t is 120, which is expected value of t squared, minus the square of the expected value of t, so minus the square of 10, and that is 20. Part D, it is given that the probability that t is less than 10 plus a is p. A is in between 0 and 10. You need to find the probability that t is in between 10 minus a and 10 plus a. Let's look at the graph of the probability density function again. We have a quadratic that is perfectly symmetrical. This is 20. This is 10 here. That would be t and 0. And we have f of t. We are given that the probability that t is less than 10 plus a. 10 plus a, let's say this is 10 plus a. And we are given that the probability t is less than 10 plus a. That is the area of this shaded region here. This area will give us probability t. Sorry about that. Let's write this properly. Probability t less than 10 plus a. This is given by p. If this region is p, then we know that this region is 1 minus p. Total probability is 1. Total area under the graph must be 1. So this region must be 1 minus p. We need to find the probability that t is in between 10 minus a and 10 plus a. So for t in between 10 minus a and 10 plus a, let's look at the region that we need to find. That is 20. Okay, that is 10. So if this part is 10 plus a, this 10 plus a is a units away from 10, then 10 minus a is a units away from 10 as well. What we are required to find is the area of this shaded region here. This shaded region will give us the probability that t is in between 10 minus a and 10 plus a. That is what we want to find. This unshaded area from the previous diagram, this unshaded area is 1 minus p. Then this unshaded area must be 1 minus p as well due to symmetry. The shaded region is 1 minus p minus 1 minus p. All these three regions add up to 1, but we want this region, so we take 1 and subtract the 2 unshaded region, and this will give us 1 minus 1 plus p minus 1 plus p, which is 2p minus 1. So the probability that t is in between 10 minus a and 10 plus a is 2p minus 1. Part E, we need to find the probability that t is in between 8 and 12. Unfortunately, we do not know this value of p here. Doesn't matter. the probability that t is in between 8 and 12, that is the definite integral of f of t from 8 to 12. This will give us the area under the graph, or the area under the density function from 8 to 12. So we integrate 3 out of 4,000. And what was it again? 20t minus t squared with respect to t. We can pull out the 3 over 4,000, and then we integrate 20t minus t squared with respect to t from 8 to 12. So we have 3 out of 4,000. And upon integration, 20t, so we have 20t squared divided by 2, which is 10t squared, and the second part is 1/3 t cubed. Evaluate from 8 to 12. So what we need to do now is we will replace t with 12. So you have 10 times 12 squared minus 1/3 times 12 to the 3. And then we subtract this expression when t is replaced with 8. We have 10 h squared minus 1/3 8 to the 3. That should give us a value of 0.296. Part F, give one reason why this model may be unrealistic. This model only considers time in between 0 and 20. It does not allow for times greater than 20 minutes, which is unrealistic. Well, waiting for a bus for 0 up to 20 minutes is unrealistic. Sometimes there are buses, they are late. You may have to wait 30 minutes, 40 minutes, an hour